Good morning and welcome to everybody. We are here to listen to Marco Tantardini. He is an engineer, a scientist, an entrepreneur, and a pioneer. He holds a Bachelor of Science in Aerospace Engineering from Politecnico di Milano and received a Master of Science in Space Engineering from the Delft University of Technology in the Netherlands. And he also studied in the Politècnica de Catalunya in Barcelona, Spain. Before graduating, he worked as assistant to the executive director at the Planetary Society in Pasadena, the world's largest and most influential public space organization group. And he was also visiting scientist at the Mission Design Center of the NASA Research Center, AMES, in Mountain View. In 2010, Marco built the strategy and the core of the team that led to the asteroid retrieval mission at the Keck Institute for Space Studies at Caltech in Pasadena. And in 2011-2012, he promoted this project to aerospace executives and governments. In the same couple of years, Marco also acted at the ESA contact point for the Kiss Arm study, reporting to the ESA headquarters in Paris. In spring 2013, the White House and the NASA headquarters backed ARM, renamed Asteroid Redirect Mission, as the new strategy for America's human space exploration, recognizing Marco's key role in it. Through KISS, Marco keeps exploring opportunities of international collaboration connected to the NASA ARM program, and he is advisor to the president of the Italian Space Agency for new activities for human space exploration. Marco is an Aspen Junior Fellow at Aspen Institute, Italy, and the partner of the International Startups Incubator and Accelerator, iStarter. He is founder and chief executive officer of Drone Systems, a startup creating an ecosystem for the unmanned aerial vehicles. Marco was featured on the May 2014 issue of Popular Science. We welcome Marco and try to listen from him of these marvelous achievements.
Thank you very much. So, good morning. I am Italian, so I could speak English, but I was told that I could speak, I can speak Italian, but I was told that I could give this presentation in English, and so I will try my best to speak slowly. And we have some slides, we have some animation, so it's Saturday morning, so let's try to have something that is fun. My presentation is going to be about human space flight, about the future of NASA, so I think it is something that is not that boring, and I hope you're going to enjoy it. Let me put there. So as you know, the title of this presentation is You Can Do It, How Internet Enables Entrepreneurship in Science. And so it wants to be a little story of how this program that has been renamed NASA Asteroid Redirect Mission started in 2010. I was born in Italy. I was born in Cremona, and I studied there at high school. And in 2010, I was thinking of this crazy idea of capturing an asteroid to solve a problem that NASA had for the future of human exploration after the International Space Station. And so from there, I managed to assemble a team around me that took me to California. But first, I want to show you something that I believe in very much. It's a little video. Steve Jobs gets quoted too much. I didn't like it that much, but I like very much this, what he says in this little interview. So let me start.
No, I've actually always found something to be very true, which is most people don't get those experiences because they never ask. I've never found anybody that didn't want to help me if I asked them for help. I always call them up. I called up, this will date me, but I called up Bill Hewlett when I was 12 years old, and he lived in Palo Alto. His number was still in the phone book. And he answered the phone himself. He said, yes? He said, hi, I'm Steve Jobs. I'm 12 years old. I'm a student in high school, and I want to build a frequency counter. And I was wondering if you had any spare parts I could have. And he laughed, and he gave me the spare parts to build this frequency counter, and he gave me a job that summer in Hewlett-Packard, working on the assembly line, putting nuts and bolts together on frequency counters. He got me a job in the place that built them. And I was in heaven. And I've never found anyone who said no or hung up the phone when I called. I just asked. And when people ask me, I try to be as responsive, to pay that debt of gratitude back. Most people never pick up the phone and call. Most people never ask. And that's what separates sometimes the people that do things from the people that just dream about them. You gotta act. And you've got to be willing to fail. You've got to be willing to crash and burn. With people on the phone, with starting a company, with whatever. If you're afraid of failing, you won't get very far.
I don't know how much you understood of that. And I reported even a little quotation under the video. So what you said is that if you are afraid of asking, you won't get very far, right? And this is indeed, something that I learned myself too, and that I lived into this journey for this study that became the NASA Asteroid Redirect Mission Program. So in 2010, in the US, NASA and even Obama, the new president, were thinking, what after the International Space Station? So the International Space Station is our present for human space exploration, mostly operations. It was conceived during the Cold War, so during the Reagan administration, but it was built starting in 1998 during Clinton administration, and but it's going to be over. Likely, it's going to be over around 2024. And the International Space Station is quite close to us. It is just 400 kilometers above our head. So yesterday I was driving from Cremona to here. It's that distance, so it's quite close. The moon is 400,000 kilometers, so it's much farther. And so they were wondering, what next after the International Space Station? Because governments have to push the barriers, the frontiers, but you have to make a program that is sustainable. If you say, I want to go to interstellar space, that is a cool topic for a movie, but technology does not allow us that. And so, this is typical charts that are very complex. I don't want you to look into that. But in the 2004, during the Bush administration, they were thinking, we will go back to the moon and build a colony on the near the South Pole, so that we will send astronauts there, we will send habitable models, we will send rovers, and we will do it with our international partners. And so I want to show you another little animation, because animation are always nice. So this is the future that in 2004 they were thinking of.
We leave as we came, and God willing, as we shall return. We shall return. We shall return.
Yeah, they said we came to the moon, and we will get back. We will return. That was said by the last astronaut on there, of Apollo 17. And so 10 years ago, they were thinking of starting having robotic missions to get some data. And then with the rocket that they were building back then, called Ares, they were thinking of developing this rocket that is similar in terms of the shape to other rockets. But to do that, we should use the lander, but we don't have the know-how now. We're completely lost. We don't know how to build it now, so it takes much money. And then we would build an infrastructure for a colony there, these models, system then to get back to the Earth. A little rocket jumps the surface to get back. So yeah, 10 years ago, that's what we were saying. The journey begins now, and that's the same we are saying now with a different program. So we'll see at the end if we end up at the same, with the same failure. But the fact is that so they were having this NASA program to go back to the moon. But the problem is that if you want to do things, you have to allocate the resources. So you have to have a good project management to finance it to the right level. Otherwise, you just get behind schedule, and you realize after a few years that you spent much money, that you are behind schedule, and you will not manage to meet the goals that you set yourself, and so it's a mess. And that's what happened when Obama was elected in 2008, and so, and he nominated a committee to review the NASA strategy, the American strategy for human space flight after the International Space Station. And they realized that, they saw that rocket, that orange rocket that was in R&D those years. It was a 9-year-old program, and it was underfunded, and they realized that they were burning billions of dollars, but they were not enough. And so they decided to cancel that program. And then also for the destination, they realized that a colony on the moon is something that is very interesting, but it was too complex considering the budget that America has. We are not in the Cold War anymore. There is not a race to the moon or to space, even if some say, that time was with Russia, some say that these days we might have this battle with China, but it is not true. They are very much behind. And so in principle, it's a sort of monopoly of the United States, while Russia is very good in providing the infrastructure to go to the low Earth orbit, that is where the International Space Station is. But to go farther, they lack of the people, because after the collapse of the Soviet Union, most of the scientists moved to the United States, and there's a generational gap, and so and also there's a financial problem there. So this committee realized that the rocket had to be cancelled, and we had to come up with a flexible path. That means that instead of saying, let's go to build something very complex and go straight there, we should do things step by step and achieve incremental goals. And in the meantime, through these incremental steps, develop the technology, do missions, and then move on. So having Mars as the horizon, so as the final ultimate destination, that is in mathematics is called like an asymptote. It's something that you point, but if you would not try to get there straight, right, you get very close to it. So it is something that's going to be in the future. But now we should develop something that is sustainable, and so they were proposing of having developing a capsule that in the future will have astronauts on board, that as a first test a man, so without astronauts, about the moon. And this capsule indeed had already a test in December. You might have read something on newspapers. The test was first performed about the Earth with a high and very elliptical orbit. And in a few years, in a couple of years I think, when the rocket is ready, the new rocket that NASA is developing, but we'll see later, they will launch it unmanned about the moon. But then the fact is that, so if you have a lunar flyby with astronauts, it is a 10 days mission. And it, as said, is very far, because so far we are used to go to a destination that is just 400 kilometers from where we are right now, and the moon is 400,000 kilometers. So it is already a big step forward, even if we already did it in the late 60s. But then having Mars as the goal, the idea was to have these incremental steps, like going to what are called Lagrange points, that are points of equilibrium between, for example, the Earth and the Moon. We will see them later. Or go to an asteroid. And this was where indeed Obama was maybe even badly advised. Because as you can see here, if you want to go to an asteroid in its natural orbit, so without grabbing it robotically and put it in closer, but if you want to go to an asteroid in its natural orbit, because of the physics, because of the shape of the orbit, because of the energy level of these objects in space, it will take 6 months. So to go there and come back, it will be a mission in deep space for 6 months. And it is very complex, also for the systems that are developing, and so you would need to invest much more than what NASA is investing in right now. This is just to show you the investment that NASA was doing in the 60s in preparation of the Apollo program, and you see it was very big. But then it went down because after they conquered the moon, the interest went down, the public interest went down. And so now we have a budget that is flat. So we have we should find a path that is sustainable with a budget that is flat. And also, sometimes we hear that for human space flight, NASA as the asteroid now as the destination, while Europe wants to go back to the moon. But after all, the leader is the nation or the agency that allocates most of the resources. And frankly, for human space flight, that is NASA, because the NASA budget every year is, per year is about $17 billion, and for human space flight, it is about $7 billion, while for ESA, the total budget is €4 billion, and for human space flight, it is 300-something million euros. So, as we saw yesterday, I was here when Akamatsu gave the terrific presentation about Rosetta. So, here in Europe, we are able to do great things, mostly for scientific robotic missions. But for human space flight, we have to work with an American partner, because they are so strong and they are allocating so much resources that they are the leaders in this. So we have to cooperate with them, but provided we do not increase drastically the budget, that's not the case. We're not going to increase drastically. So NASA is going to set the path and the destinations. And so Obama in 2010, after that review, that commission that he nominated in 2009, said, we are in a not sustainable path, we are spending too much, we have to kill that R&D for that rocket, and the moon base is too complex, too expensive. So Obama said, okay, so maybe we have to develop a different rocket, not a family of rockets as we were thinking that times. And so we will develop a heavy rocket that will take astronauts in deeper space. But instead of thinking about a moon colony, we should have Mars as our ultimate destination. But we will start having a mission to an asteroid in 2025 and send astronauts there. And then he said, I expect in my life to see American astronauts to go nearby Mars. But so here the fact is that it probably was badly advised, because as we saw earlier, going to an asteroid, it takes 6 months. And the problem is that as you can see also here, these were, so NASA, after that announcement from the president, of course, reacted, and they started working on proposals for missions to go to asteroids. But the fact is that asteroids that could be reached by 2025 are not that many. And as you can see there, for the mission duration, it takes, I mean, it's going to take many months. And there were just few targets. And so the problem is that if you miss that target, so if your program is delayed and you don't manage to launch when you're supposed to, it's a all or nothing approach. And moreover, this is the capsule that I was telling you NASA is developing. They already tested it in an orbit about the Earth last December. This capsule that is going to be what astronauts are going to use in the next decade is designed to have 4 astronauts for just 25 days. One thing is to have goals, but one other thing is to consider those goals with the hardware that you are developing. So 6 months with a capsule that we're going to have that can have people surviving in there for 25 days, I mean, it doesn't fit. And this is the rocket that NASA is currently developing. So in 2010, there was this big confusion. So President saying, let's go to an asteroid. But at the same time, NASA studying that, but could not find a solution. And so there was a huge opportunity, and that's where I tried to plug in a bit. So I thought, why not merging different interests for science, for technology development, and for the future of human spaceflight, and thus have a robotic mission that is very flexible, because a robotic mission, as we know, can fly for many years, and since they don't have people on board, can go to very complex environmental conditions, and it's all right. And so have a robotic mission that's going to fly for much time, is going to capture somehow the asteroid, and that is how to capture it was one of the challenges that we had to solve, and take it closer so that the capsule Orion that NASA is developing, that can have 4 astronauts for 25 days, can fit with that, so that can take astronauts to the asteroid. So that time, that proposal. So I was in Italy, and I was in my town that summer. So I came. I had some brainstorming, and then I prepared some slides that I presented at Caltech that fall, and I called that Sisyphus victorious, because in mythology Sisyphus was always doomed to, he was pushing a rock and was always doomed to fall back with a rock. So we were thinking this time he's going to make it, and we were indeed I was calling that for science. So there was science involved, because the fact is that asteroids are of interest also because they are also a potential threat, near Earth asteroids at least. But there are asteroids that have an orbit that crosses the orbit of the Earth. So someday might have an orbit that is going to impact the orbit of the Earth. And so we got a developed plan and the technology to react in case there is this threat. By the way, next week here in Italy, there is a very important international conference that 2 years ago was in Arizona, and it's going to be in Frascati. So you're going to read about that. And all the international community is going to meet from Monday to the end of the week to discuss about planetary defense. And so it's going to be something very interesting. If any of you is going to be in Rome at the Italian Space Agency, they're going to be on Wednesday evening, a radio show by the Planetary Society, that is this non-profit organization where I work with, and it is free. So I don't know, we are in Foligno, but if any of you happens to be there, well, that's cool. I forgot that's cool. And so the fact is that I was saying, these days, if you want to contact someone, it's quite easy and it's quite cheap. So for example, if you, so the method that I was using to try to develop this, you know, from my personal idea into a team, into a program, was that I had to learn more, so I was using Google to collect papers and to learn more about this subject. And then in papers at the end you find references that are, you know, that are a list of papers of people that already studied something close to it. And then you can try to find them, and you Google their name, you can find their email sometimes. And for NASA, for example, it's very easy. There's a website that is called people.nasa.gov. And for example, if you want to find the contact of their boss, the administrator, you just type the name and you find his email and his phone number. Then, of course, if you write him an email, he will receive it, but sometimes, most of the time, he might not reply. But it's not, if you insist and if you have something good to propose, they will get back to you. And also, if you want to call, I mean, I guess that, you know, before Skype, it would have been very expensive. But, you know, if you use, for example, Google Voice, you can call any landline number in the US being here, and it is just 1 cent per minute. So it's very accessible. So if any of us, with internet, I mean, you can really be at the very center of the world, and if you have an idea, you can really gather people around you. And so that's how, so that summer, I tried to involve the NASA people, mostly from the Jet Propulsion Laboratory in Pasadena in Los Angeles. That's where they develop robotic missions like the rovers to Mars. And we found a place where we could start meeting and moving this concept. That is called the Keck Institute for Space Studies. That is a think and do tank on Caltech campus. And so we applied and we were selected. And so we had, in fall of 2011, we had a workshop there. We met for a week, and this is the Athenaeum, that is the club of Caltech where Einstein and Oppenheimer and others used to go. And I mean, and so this was the group that we assembled, and it's a very diversified group. So, for example, this guy is Rusty Spikert. He was an Apollo 9 astronaut. So he didn't, since I mean the first person that walked on the moon was from Apollo 11. He had just a flyby, but he was part of the Apollo era. This person was an astronaut on the shuttle, I think in 1992. You might have heard of crazy companies that want to mine asteroids to extract resources, and one is called Planetary Resources, and the president is Chris Lewicki, who was part of our study. Then the most important researcher in this crazy field of asteroid mining is John Lewis, professor from Arizona, and he was with us. Then you might remember that Pluto used to be considered as a planet of a solar system, but then it was downgraded as a nanoplanet. And the work that modified this classification was done by Mike Brown of Caltech. So indeed, he wrote a book called How I Killed Pluto. And so, for example, this person is the head of the observations of asteroids. It used to be, because he just retired, for NASA. So it's a very diversified group. It was very interesting. And so we met, you know, that fall of 2011. We met there. We started, you know, discussing, and we had different backgrounds covered, like, you know, how to go to the asteroid, so how to design the trajectory to go there. And so, for example, we had researchers that are expert on that. For example, Nathan Strange led the design of the trajectories of Cassini near the moons of Saturn, or that challenge is a new one. Because an asteroid, so if you think of a 10-meter asteroid, it can be 1,000 tons, and the International Space Station is half of that mass. It is 450 tons. So and moreover, asteroids are also rotating, and so you really have to find a way to approach it, and to rotate with it, and then to have a system that is going to hold it. And for example, there was Brian, that is a robotic expert. So we worked on this. It was quite interesting. And then, so from the idea to the team, and after the team came with some solutions, we wrote a report in 2012, and we started, and we found that the results were promising. So we found that the capture mechanism could be developed, and also some experienced scientists and engineers were saying that moving an asteroid was not possible with current technology, but it was a subject that was not that much covered in literature. So we showed that actually you could. And so we gave this presentation, and we started, talking also in Washington with the NASA headquarters, and then we started, having people and newspapers and policymakers know about this concept that could solve a problem that NASA and the Obama administration had. And so in December of 2012, on the Aviation Week and Space Technology, that is a weekly magazine that covers aerospace and space, there was a nice article showing that the message, reached the right people, and they were saying, bring the mountain. So they said, if it is so challenging and so hard to have astronauts go to an asteroid, because we are not going to have a technology yet, why not maybe moving one closer? And indeed, 2 years ago in April, when the White House proposed the budget for NASA for the year 2014, they announced that the ARM, this asteroid redirect mission, was the proposed NASA strategy for human space flight. And after all, so it was, for me, it was, quite interesting to check my slides, for example, of 2010, when I gave that little presentation of Sisyphus Victorious at Caltech, just to 4 or 5 professors there, and they were saying, just in terms of like something that you write on paper, like some bullets, they always say, if we do this research, probably we have to focus on 3 main subjects. The scientific part of how to identify asteroids that could be destination for this robot to capture it. Then we should study the robotic mission, so how the robot should be, how it should capture it, what the trajectory. And then the third part is, once we move it closer to the Earth, what will astronauts do there? And indeed, that was also what NASA has been showing since then. The 3 branches are identify, redirect, and explore. So indeed, they say, the first part is driven by science. So we have to point telescopes and to have ground and space-based asteroid observation and detections to find the right targets that suit for our purpose. And then once we find the right targets, we should have a robotic mission that somehow should capture this asteroid and then once it is moved, we have to study how the astronauts will interact with that. So then in terms of how the robot will look like, this was the very first sketch that the team at Caltech made. So we are thinking of having, the spacecraft is this little thing. It's called, it's a bus. It's just a cylinder that is put into a rocket when it is launched, and this is just on the side. Once it is in space, you need power, and you use the sun, you need solar panels, so you deploy solar panels, and then you cruise towards the asteroid. Once you are nearby the asteroid, we were thinking that if you want to capture an asteroid in its natural orbit, a small one, because there are some reasons, you cannot capture an asteroid that is 1 kilometer wide, or, you know, or 300 meters wide, for few reasons. Of course, I mean, it is so massive that you will need too much energy to bring it back. And so, again, it will not be feasible with the technology that we are developing. And another reason is that also, provided that you manage to capture such a big asteroid and move it, but let's consider that you make all the mistakes that you should not make, and you put it in a trajectory that goes towards the Earth. Well, such a small asteroid, up to 15 meters, they are small enough, and so in case they go towards the Earth, the atmosphere will burn it. So it is not a potential threat. But a bigger one, as we saw in 2013 over Russia, when in February there was, you know, that asteroid that was probably it was 30 meters to 25, 30 meters big. It had that big shock wave that destroyed, destroyed even, for the shock wave, destroyed windows. Or even 100 years ago in Siberia, there was an asteroid that was 60 meters wide, and it destroyed an area as big as New York City. I mean, dinosaurs got extinct because a much bigger asteroid hit the Earth. So the fact is that we have to start with little asteroids, and because we are able to move just smaller ones, because when you start doing things, you should do things that even if you have multiple failures, still it is safe. And after all, I mean, the fact is that people that were not liking this proposal were saying, well, President Obama said, let's go to an asteroid in its natural orbit that is 60 feet, 100 meters wide, whatever. And because we always remember that when astronauts went to the moon, they were walking there. But asteroids that do not, they're much less massive, so they do not have that much gravity. And so if it is 10 meters, or if it is 500 meters, it doesn't make much difference. So what you will see is that the astronaut interacting with the asteroid will not walk over it at all. It will do like when you see people doing these extravehicular activities near the International Space Station, or when, for example, in the past they fixed the Hubble telescope. It's like, you know, diving and swimming nearby. So of course, in terms of a television event, having a man near a bigger asteroid is much interesting. But this is what we can afford right now. And so we are considering, and also NASA was considering two options. One was considered the option A, that has been superseded by the option B, because NASA just selected the option B, as I will show you later. And the idea was, let's have, so this robotic mission, this was the cylinder I mentioned earlier, to evolve in this shape. That is a robot that is going to have solar panels, is going to go towards an asteroid, and then it's going to have a big Kevlar bag that is gonna you know, swallow the asteroid in it, and then you're going to close the bag, and then you're going to send astronauts. At the end of this presentation, I'm going to show you another animation, so you will see it all. And so once we have astronauts there, with that Orion capsule that NASA is developing, we will send them where the asteroid is, near the moon. This capsule is gonna attach. The technical term is dock. So it's gonna reach the robot, and then astronauts will go out of a capsule and interact with the asteroid. Another concept was if one option is to find a small enough asteroid so that a robot could, in its natural orbit, so that a robot could find it and capture it. But another option is, let's go to a much bigger asteroid and let's find a rock on its surface, and then have the same sort of spacecraft that is a little bit modified, but the main rationale is the same, that is going to go down and is gonna take one of these rocks, and then it's going to depart from the main asteroid and then go towards the moon. So during the study at Caltech, we were analyzing both concepts, but the option number one was the one that was called option A. It was take an asteroid in its natural orbit. However, there are challenges for both the cases. The challenge for the option A is that if you want to find and capture an asteroid that is just 10 meters wide, it is very hard from the ground and from space-based observation to identify it and to decrease uncertainties related to that. Because what we do is that we use telescopes or we use radar observation when the asteroid is not too far, and we try to look at it, but we have uncertainty. So we say the asteroid should be from the light that it reflects. We say it should be about 10 meters, but we have an uncertainty that might make it 25 meters big. And so the scientific team was confident that we could decrease the uncertainty for this option A enough to have the option A feasible. But then just a few weeks ago, the headquarters made this decision of choosing the option B, that is, you have asteroids that are much bigger, so that are much easier to be observed. And to few of them, we already sent a spacecraft because, for example, and these are, for example, potential targets that NASA is considering. Itokawa is an asteroid that is quite big, that was reached by a spacecraft launched by Japan that was called Hayabusa. And so it was very well characterized by that robot when Hayabusa was nearby Itokawa. Bennu is another asteroid that is going to be reached by a robot, by a scientific mission led by NASA that is called OSIRIS-REx. And so we expect that by the time we want to launch the asteroid redirect mission robot, that is going to be around 2020, we are going to have a good understanding of the surface of this asteroid. And the scientists have been able to observe very well this asteroid. Unfortunately, asteroids, once they become famous, they get a decent name. But otherwise, they are classified with the year they are discovered and with some letters. So, and this is there is this 2008 that was discovered in 2008, and an EV5 that is considered to be probably the most promising destination for this spacecraft. That is, if you look at it in perspective with respect to a person, so the spacecraft is going to be, that big. And then, so once we capture that asteroid, where are we going to take it? And so as I said, so far, we've been here these years at the International Space Station, but as you can see, it is very close to the surface of the Earth. And geosynchronous satellites that are satellites of Sky, of DirecTV, are much farther, but still the moon is much, much farther, and asteroids in their natural orbit are even farther. So the idea is that once we capture the asteroid, we are going to use also the gravity of the moon to have the robot with the asteroid be captured in what we call the distant retrograde orbit. That is a very wide orbit, this yellow one, about the moon, so that then astronauts from the Earth will go here and will interact with the asteroid, and then they will get back. And this is an interesting picture, also for mathematics, because this is what is called the gravity well. Well is pozzo, and it means that when the closer you are to a massive body, the harder it is to climb. But then once you get far enough, then the energy you need to go farther is the increment you need becomes little. And so if you are on the surface of the Earth, you are at the very bottom of this gravity well, and you have to climb. Even if the ISS is very close to the surface of the Earth, but still, I mean, that part is very steep, so it takes much energy to get up there. And if you see the geo, it is already up here. So the hard part, and this is why we are using rockets, the hard part is to go from the surface to beyond geo. But then once there, it is much easier in terms of the energy needed. And then, so the idea is that, again, that through this program, we are going to develop a technology incrementally. And so that, so one technology that NASA is developing that is going to be needed also for the journey towards Mars is what they call solar electric propulsion, because rockets, for example, use chemical propulsion. So like you burn hydrogen with oxygen or kerosene, but they are very inefficient. So you need very much mass of propellant to move something. And so since the asteroid is very massive, if you use a very inefficient power system, you will need so much kerosene or oxygen that you will need a huge robotic spacecraft to move the asteroid. So we would not manage to do it. But there is a very efficient system that uses the sun light with panels to accelerate xenon. This is called solar electric propulsion. That gives a little, so that is gives a force, a thrust that is very gentle. So it is not that strong, that impulsive as chemical, but it is very efficient, and it keeps giving you that for much time. So that it is not that good if you want to have a journey that is short. So if you have, for example, people on board because you want them to get back home soon or to reach a place soon. But for robots, that's very good. And so also when we are gonna send logistics or towards the cislunar orbit or towards Mars, that is a system that is highly needed. And so again, so this is to show you an overview of this first step, the asteroid direct mission. This first part is to have the robotic spacecraft that is going to reach a bigger asteroid. It's going to characterize it further when it's there. Then it's going to go down, grab a rock out of it. Then it's going to perform. So because two objects with mass attract each other, we are going to perform what we call enhanced gravity tractor technique to try to modify a little bit the trajectory of the bigger asteroid. The idea is that this is not the case for the asteroid that we are going to, but if you find an asteroid that might pose a threat and it might hit the Earth in the future, a technique that might be interesting could be to go there, augment the mass of your spacecraft, and then fly around it or nearby it and give it a little acceleration that is enough so that once the asteroid gets nearby the Earth, instead of hitting it, it passes just very close. So that is a test that this mission will also perform. Then the spacecraft with the asteroid will go about the moon, and then we will send astronauts around 2025 so that they interact with that. And this is so that this flexible path that currently NASA is considering for the journey to Mars. So far we've been having extended missions at the International Space Station. So like our Italian astronaut has been there for 6 months. Now American astronaut with a Russian, I think, they're going to have a 1-year-long mission. And so, but we've been to this low Earth orbit for a while. And in the meantime, NASA is going to have commercial players bring also astronauts to the International Space Station. So they founded, for example, SpaceX and another company that so far they already take cargo, so they take food and they take experiments up there. So that NASA has been focusing on pushing the frontier, and so they are developing this new rocket that is gonna be needed to go further towards deep space. And they are developing this capsule that still, it is not enough for a few months, for astronauts for a few months in deep space. But with ARM, we are placing first an asteroid. The idea is to place an asteroid in cislunar space so that 2 astronauts, so not 4, because still the mission with astronauts to cislunar space is going to be a little bit more than 25 days. So instead of 4, we are going to have at the beginning 2 astronauts go to the moon where the asteroid is and interact. But then with the same spacecraft, with little modification, we could use it to move in space what we call in-space habitat, that are modules that are similar to those of the International Space Station, but that are designed for different environmental conditions, especially for radiation and for the heat. I mean, for temperature and the surrounding. And by the way, for this, Italy is very strong and it's very well positioned because I forgot to say that half of the habitable volume of International Space Station has been built in Turin by Thales Alenia Space. And that's why also one of the reasons why we've been having astronauts that have very long missions for 6 months on the ISS, because it was part of a bilateral agreement that in the 90s NASA and ASI had, so that Italy provided some of these models, and then the American partner provided slots for Italian astronauts to spend much time there, operated through the European Space Agency. And so then once we have this in-space model, then we are gonna, in the future, we are gonna use it to go towards Mars. So this is the same chart that. So maybe I can show you something like this again. So we are gonna have astronauts to go about the moon, and then we are going to have another rocket launch an habitable system after the asteroid direct mission. The 2 will assemble in the same distant retrograde orbit I showed you earlier, where there was that gravity well, and then astronauts will go towards Mars, but it's going to be, in a few, I guess, NASA says in the 30s. I am a bit skeptic. I think maybe 20 years, no, but more than 20 years. And then the first probably because it's not going to be Mars as a surface, because it is very challenging to go down. So you have to decelerate. You need the technology that is called as entry, descent, and landing. You have to decelerate and not crash. And then once you are there, you have to have the technology that a little rocket that takes you up again. So NASA is thinking of Phobos, one of the moon of Mars, as what comes as the first part of his journey towards Mars. And then on the way back, astronauts would be, for the long journey towards the moon neighborhood, they will be into this Orion with this exploration augmentation model, this habitation that I mentioned you earlier. And then the Orion, the capsule, will go back to the Earth, while that habitation model will go back toward the moon and will be used again. So to conclude, I want to show you the animation that NASA has made about this very first step, that is called the Asteroid Direct Mission. So let's start. Characterize it to be sure that there are the right rocks that we're going to try to capture. And slowly it will go down to the surface. Microspines to act with some force on the rock and capture it, and then jump off it. Set the gravity force is very little, so we need a little impulse. Perform that planetary defense test, as I mentioned earlier. So this augmented mass is going to stay nearby the asteroid, and we're going to check if she says we give the bigger asteroid a little acceleration. There might be a technique that might be there. And then once that test has been performed, it's gonna go towards the moon. And in the meantime, we will also perform science, so that we're gonna have the robot, we're gonna have sensors, so even while it is towards the moon, the sensor are going to analyze the rock, they're going to send data. So there is this first scientific part, but then we're going to add the exploration part. So this is a new rocket that NASA is developing. It's called the Space Launch System, and so yeah, and with Orion. Two astronauts in there that are going to go into this high orbit. They said that they're going to dock, so we're going to attach Orion automatically to the robot that captured the asteroid, and then the astronauts are going to interact with the asteroid, having this extra vehicular activity. Also collect samples, and they will be, because the orbit is a very high orbit about the moon, they will be even much farther than the moon, so it's going to be a first step even further. And then they will collect samples that are going to be used also by scientists, I think, not just in the US, but the world agreements that NASA is going to have, and it's going to be. This asteroid is going to be locked about the moon for definitely more than a century, because the orbit is very stable and it is one of the reasons why it is chosen. And so we are going to have multiple missions there, even then private companies, if they want to get there, they can. It's going to be there. And then the Orion is going to take the astronauts back. And that's it. So yeah, the hour is over. I hope it was not boring. I tried to give you an overview of the problem that NASA had in the past. And truth be told, I mean, there's much, unfortunately, it's all about politics. So it might be, because very many people don't like this proposed NASA program for the asteroid radioactive mission, especially scientists some scientists really hate human space flight. And they think that if you kill human space flight, you're going to have more resources for pure science. But that is not the case. So the fact is that after the International Space Station, we have to find something for the human space flight that is sustainable. Because if we stop doing that, we will lose the know-how. We will have new generation not knowing more, but knowing less. And so this is what currently NASA is proposing. But in any case, I think that in case, for example, politics in a few years might decide to cancel this asteroid radioactive mission, still what I said about manned mission using the same spacecraft, about the moon deploying these habitable models, that's going to be something that still we're going to see. So hopefully. And the fact is that here the deadline for this mission is very close, because since we want to have astronauts to visit this asteroid in 2025, we want this robot to be launched around 2020. And it might seem far, because it's 5 years, but since these are complex programs, it is very close. So soon we should know more. So thank you very much. And by the way, if you have any questions.
Yes, many thanks to Marco Tantardini for both for the scientific and technological content and for the English lesson. There is a time only for one question, and English, of course, is preferred, but...
Okay. Thank you, Marco, for the presentation and for the mission, first of all. My question, I have a question and a curiosity. The question is, like in Rosetta mission, probably the identification, selection, and classification of the rock that will be grabbed by the module would be an orbit by the module itself, based on X-rays, imaginary, and so on. Which are the margins of errors, the technology malfunction, potential technology malfunction that could drive to a failure of a mission, like it was in Rosetta. And the curiosity is, you told about the microspines that will grab the rock. Which is the technology beyond that?
Yeah.
On that, how is it based? How does actually work it? Thank you.
So thanks for the question. For the first part, well, what you just asked indeed drove very much the decision to choose between option A and B. So for the option B, NASA feels more comfortable in having the uncertainties decreased enough for the target asteroid, because they say for Hayabusa, since already there was a spacecraft that went there, so there were already proximity operations that very well characterized the rock. Same for Bennu, because there's going to be this OSIRIS-REx, so it's going to do the same before we launch but still, for that 2008, whatever are the letters, I never remember, from the ground, because that is a big asteroid, they already managed to have very detailed observations, and they are confident there are rocks on there. So then to identify which rock we should go grab, that's going to be something that is going to be chosen and identified once the spacecraft is nearby, as indeed in the animation there was that part at the beginning where the robot was orbiting about the asteroid, and with those green rays it was analyzing it. In terms of, I mean, it is a very complex mission, and of course well, many things could go wrong, but I've been told that, for example, compared to Philae, I mean, the system is totally different. So, of course, one naive comment that I also made myself at the beginning when we was having discussion is, since Philae had so many problems in getting on the surface of that comet, it should clearly show us that it is very challenging and for the option B. But the fact is that Philae, as even yesterday they said, it was not very much controlled. They were just throwing it down. And here, this spacecraft is going to be, I mean, it's like throwing something and hoping it's going to get there and stay there, or driving something towards it. So this spacecraft is very complex. It has all the sensors. And so for the proper selection of a small boulder and to get on the surface, NASA is confident that the design is robust. Then, of course, you can always have some system that they fail. And so, for example, if the capture mechanism fails, or if the rock that you thought was loose enough to be moved up is not, you might try to go to another rock. So they are thinking of something robust. But of course, in any active system, there's risk. Then for those microspines, honestly, I must admit that I do not know enough. I remember that because also in my field is mostly in trajectory design, and that comes mostly from the robotics part. It was a technology that was shown at the very first workshop we had at Keck Institute at Caltech in 2011. I remember there was a student, or a PhD or postdoc, that came in and he showed his research about these microspines, even to these robotics gurus that were very experienced, and they showed very much interest. And after a while, I saw that it was included. So honestly, I mean, I can find out more. I can, if you give me then later a contact, I can send you something. But I do not know enough. I just know that they have these microspines that are able to really. And they've been testing it very much already. And it was, when you see some videos of this technology tested, it is quite impressive. Any other question?
I fear we have to
leave.
To end, because there will be another conference in 11 o'clock. So many thanks again to Marco Tantardini.